let's say we have a circle, and then we have a diameter of this circle. Let me draw my best diameter. That's pretty good. This right here is the diameter of the circle, or it's a diameter of the circle. That's a diameter. And let's say I have a triangle where the diameter is one side of the triangle, and the angle opposite that side, its vertex sits someplace on the circumference. So let's say the angle, or the angle opposite of this diameter, sits on that circumference. So the triangle looks like this. The triangle looks like that. What I'm going to show you in this video is that this triangle is going to be a right triangle. Is going to be a right triangle. And the 90-degree side is going to be the side that is opposite this diameter. I don't want to label it just yet because that would ruin the fun of the proof. Now, let's see what we can do to show this. Well, we have in our toolkit the notion of an inscribed angle, its relation to a central angle that subtends the same arc. So let's look at that. So let's say that this is an inscribed angle right here. Let's call this theta. That angle theta. Now let's say that that's the center of my circle right there. Then this angle right here would be a central angle. Let me draw another triangle right here, another line right there. This is a central angle right here. This is a radius. This is a radius. This is the same radius. Actually, this distance is the same. But we've learned several videos ago that, look, this angle, this inscribed angle, it subtends this arc up here. It subtends that arc up there. The central angle that subtends that same arc is going to be twice this angle. We proved that several videos ago. So this is going to be 2 theta. It's the central angle subtending the same arc. Now, this triangle right here, this one right here, this is an isosceles triangle. I could rotate it and draw it like this. If I rotated it, I could draw it like this. If I flipped it over, it would look like that, and then the green side would be down like that. And both of these sides are of length r. This top angle is 2 theta. So all I did is I took it and I rotated it around to draw it for you this way. This side is that side right there. Since its two sides are equal, this is isosceles. So these two base angles must be the same. So these two base angles must be the same. That and that must be the same. Or if I were to draw it up here, that and that must be the exact same base angle. Now, let me see. I already used theta. Maybe I'll use x for these angles. So this has to be x, and that has to be x. So what is x going to be equal to? Well, x plus 2 theta have to equal 180 degrees. They're all in the same triangle. So let me write that down. We get x plus 2 theta all have to be equal to 180 degrees. Or we get 2x plus 2 theta is equal to 180 degrees. Or we get 2x is equal to 180 minus 2 theta. Divide both sides by 2, you get x is equal to 90 minus theta. So x is equal to 90 minus theta. Now let's see what else we could do with this. Well, we could look at this triangle right here. This triangle, this side over here, also has this distance right here is also a radius of the circle. This distance over here, we've already labeled it, is a radius of a circle. So once again, this is also an isosceles triangle. These two sides are equal. So these two base angles have to be equal. So if this is theta, this is also going to be equal to theta. And actually, we use that information. We use that to actually show that first result about inscribed angles and the relation between them and central angles subtending the same arc. So if this is theta, that's theta, because this is an isosceles triangle. So what is this whole angle over here? What is that whole angle over here? Well, it's going to be theta plus 90 minus theta. That angle right there is going to be theta plus 90 minus theta. Well, the thetas cancel out. So no matter what, as long as one side of my triangle is a diameter, and then the angle or the vertex of the angle opposite sits opposite of that side sits on the circumference, then this angle right here is going to be a right angle, and this is going to be a right triangle. So if I just were to draw something random like this, if I were to just take a point right there, like that, and draw it just like that, this is a right angle. If I were to draw something like that and go out like that, this is a right angle. For any of these, I could do this exact same proof. And in fact, the way I drew it right here, I kept it very general, so it would apply to any of these triangles.